Hi, in this video I'm going to explain the concept behind ion exchange chromatography. So the ion exchange chromatography relies on the principle that our protein should have some amount of charge in it, and based on the charge of the protein we would separate. So the basis of separation in ion exchange chromatography is the charge on the protein. So here it's given a small example. Here is R plus A. Here R is actually the matrix, the beads of the matrix, which has a positive charge, and A is a negative charge attached with that matrix. Now here B represents our particular protein that we want to separate from other proteins. And what happens, this particular protein B, it exchange with A, and after that it gets bind with the matrix and it replaces A, and this is how it binds with the matrix. And after some time, if we want to elute our particular protein B, we would apply some another molecule which have a negative charge in it. So as ion exchange chromatography is also a type of column chromatography, we would try to understand how it would look like inside a column. So we have specialized beads. One of popular beads is DAE cellulose, used for anion exchange chromatography. So anion exchange chromatography means if our protein is anionic, that means in our protein we have a lot of negatively charged groups, that means a lot of acidic groups. So in this column there are DAE cellulose beads. If we zoom into the DAE cellulose beads, we can see DAE cellulose beads are actually positively charged. So if we just try to find the similarity with this equation, so these particular bead represents this R plus. So in our first step of equilibration, we would be using equilibration buffer, and say for instance this equilibration buffer turns to be NaCl. So in NaCl we have a lot of Cl minus. So these Cl minus will actually bind to this positive charge, and this Cl minus actually represents these A minus over here in this equation. And so in this step we just applied our equilibration buffer, and this Cl minus is actually represented in light blue color. And in the second step, where we would apply sample, and our sample may have some proteins which are positively charged, which are negative, which have some amount of negative charge, which have a greater amount of negative charge. And what happens, the proteins that have negative charge will replace this chlorine ion here, and it would bind to the matrix as shown here. So these green like proteins represented here would bind to these matrix, and these violet ones, they have greater amount of negative charge, that means greater amount of negative group, acidic group in them. They would also bind to the beads. But these red ones which have positive charge, they could not bind to these matrix, and this binding happens by electrostatic interactions. And after sample application, what would happen, we have to wash it with the washing buffer for elution of our protein. So first what happened, these red proteins, it won't bound with the matrix, so it would come out first. After that we have two kind of proteins. We have one protein where we have a lesser amount of negative charge, and a protein which have greater amount of negative charge because it has greater amount of acidic groups. So in order to elude this, we should use a gradient of NaCl. So even in a lower NaCl concentration, what happens, these proteins which have low negative charge would be eluted. And how this elution actually occurs, when we increase the concentration of the chlorine ion in this step, in this last step, what happens, if we increase the chlorine ion, the particular proteins that are bound here would be replaced by chlorine, and the protein would come out from that particular column. But the proteins which have more amount of negative charge, their binding would be more strong. That is why we have to use even higher concentration of sodium chloride. So if we look at a graph here, so for these red color protein, we really don't need other ways of elution. But for these particular green colored protein that have a unit positive, a unit negative charge, we can use sodium chloride. And you can see that for eluting this purple color protein even require more a concentration of sodium chloride, because these has more negative charge. This can bind with these beads in a more strong manner than the protein which have a single positive charge. And for elution of these proteins we need even more concentration of sodium. So here comes two terms. One is cation exchange chromatography, another is anion exchange chromatography. So cation exchange chromatography means that our protein is cation, and that means our protein has more amount of basic groups like lysine, arginine, etc. And to purify that particular protein or separate that particular protein, we would be using cation exchange column. And the cation exchange column popularly used is carboxymethyl cellulose. And carboxymethyl cellulose has a carboxy group, so its R thing is actually negative. So for our cation exchange, what would happen? This R would be negative and our cation would be positive, and it would be exchanged by our particular protein, and it would ultimately yield R negative, B plus, and A. So this is the basic concept of cation exchange chromatography. And for anion exchange chromatography, as we have used here the DAE cellulose, it's one of the popular anion exchange column because it is positively charged. It can bind with any negative counter ions of the equilibration buffer, and that would be replaced by other proteins in our solution. And so our protein here for anion exchange chromatography, our protein have to be anionic. That is why the term anion exchange chromatography. So our protein have to be anionic. That means it has much more acidic groups compared to other type of groups. So this is the basic concept of ion exchange chromatography. So as per summary, we can say the basic principle behind the ion exchange chromatography is protein are separated on the basis of their charge. The greater the positive or negative charge, the stronger is the binding, and hence we need to use a strong gradient of NaCl to elute that. Hope you enjoyed this video. Please like and subscribe.